as software library for modeling and simulation of solar desalination systems. www.redslibrary.com.
Hi everybody, Professor Mohammed Sharaf with you. Today we are going to talk about how can we utilize the waste gases from oil refinery plants for multi-stage flash with multi-effect desalination processes. What is the main concept? How can we run our model? Let's see. The main concept is that thermal desalination plants need large amounts of fuel or thermal power to produce large quantities of seawater, to use large quantities of seawater in order to produce fresh water. At the same time, burning them beneficial gases in the oil refineries is considered a huge waste of energy instead of using it to this negative impact to the environment and so on. Therefore, in this work, we have a novel study on the possibilities of operating thermal desalination plants by waste gases that emerge from oil refineries rather than burning these gases in the air. We have to see this. We have to utilize a hybrid multi-stage flash and MED desalination processes in order to study how can we desalinate or produce large quantities of fresh water. We have three scenarios actually. We can utilize waste gases for multi-stage flash just for desalination, and we can utilize the same source of energy from waste gases. Pardon, it is waste gases, not waste heat, to remove any confliction or something like that, or any confusion. So waste gases for MED plus organic Rankine cycle in order to desalinate or produce fresh water and power generation. The third scenario is about waste gases for only multi-stage fillers in order to work as a desalination process beside power generation. This is the third scenario, as you can see here. We have here, this is waste gases from the oil refinery. We are not going to burn these gases. We are going to utilize these gases with combustion chamber. This is the third scenario, gas turbine cycle, in order to power on gas turbine cycle. This is high pressure turbine and low pressure turbine in order to produce sufficient power for us. The study can tell us that we can produce more than 100 megawatts, and the rest of the hot gases can be used to operate the brine heater in order to power on thermally the multi-stage fillers. The second scenario is completely different. We are going to use these waste gases in order to power on the burner of the steam generator, and this steam generator have two outputs. It's exhausts to organic Rankine cycle in order to generate sufficient power for pumps and facilities and so on, and the other stream is the hot steam is going for the brine heater, and the exhausted and the condensed steam from the brine heater is going to power on flash evaporation tank. And this flash evaporation tank is the main source of energy for the MED. This is the main concept as a connection between hybrid MSF and MED. And the condensate stream of surely is going to be accumulated in the accumulative tank and repumped again to the steam generator and so on. And this is the first configuration, the simple one. We are going to demonstrate this one. We are not going to use organic Rankine cycle for power generation. It's just waste gases for the steam generator, and the steam generator is for MSF, and the condensed steam from brine heater is going to produce sufficient energy for the flash evaporation tank to help MED in order to be powered on and complete its process. Ensure the condensed steam from MED process is going to be accumulated in the accumulative tank and repumped again to the steam generator and to complete the process. Actually, this model is the design model. We're going to discover areas, mass flow rates, energy streams, exergetic streams, cost analysis, and sure, we are going to discover how much mass flow rate that should be used from the waste gases or refinery, because we are going to assign the productivity for both MED and MSF. Suppose I need to desalinate, for example, 5,000 from MSF and 5,000 meter cube per day for MED. What is the mass flow rate of the waste gases that should be used at such cases? This answer should be known by our model. Actually, we succeeded to publish a work about this in Applied Energy Journal. Because it was a novel study by the use of REDS library software. In our model, we are going to discover design limits for waste gases size, such as what is the mass flow rate of the gases, what is the size of the chimney. This is the chimney, and this is the model panel. We have steam waste gas chimney, steam generator, brine heater, mass flash tank, pump, and MED. What is the exergetic streams, and so on. Okay, let's go to our model. This is our model, and we have to double click on. But first, we have to go to the destination folder after we download our model. The model should appear like this, as you can see here. There's some information about it. Okay, as you can see here, this is this is our panel. This is our units. As you can see here, we have a chimney unit, steam generator unit, multi-stage flash, and so on, and this is pump unit. Okay, we can assign some input data, like for example for chimney, we have to assign let's emphasize a little bit. Yes, we have to assign waste gases density and dynamic viscosity. What is the tube diameter of the chimney, and tube elevation. That's tube elevation. You can control it. For the steam generator, you can assign ambient temperature, steam generator efficiency. Let's go for 80%. Design limits, waste gas calorific values. You have to estimate or calculate the waste gases calorific values. Air to gases flow ratio, you can assign it a specific heat capacity of the waste gases and cost analysis. This is brine heater. We're going to assign efficiency with the brine heater, ambient temperature, and this is some design aspects like flow speed of the steam and so on. For MSF, let's go for this is seawater temperature. I'm going for okay, 27 is fine. The top brine temperature, I'm going for 115, and last stage temperature, I'm going for 40. This is normal values. Salt seawater salinity. Let's go for 45. It's okay for Red Sea or Gulf areas, and brine below down salinity. Okay. For design, you can assign the total number of stages. I'm going for 20 stages. Heat recovery stages are 17, and 3 stages for hydrogen. And sure, you can assign what you would like, because it's a model. You can control everything. Splitter ratio, brine load, wheel friction, and so on. Some performances this is the efficiencies of pump systems, brine blew down, feed pump, brine recycle, distillate pump, and so on. Okay, for MED is the same. We are going to use this ambient temperature. Seawater temperature is the same for MSF. And brine blew down temperature, I'm going for example, 45. Let's see. And this is salinity, the same salinity, MED. This is plant productivity. I'm going for 5,000. The number of effects, let's go for 8 effects and something. This is in the condenser, efficiency, so on, pumping system, okay, efficiencies. And this is flash tank. We can assign here, so sure, ambient temperature, and this is a steam pressure. Just I think 0.35 is or 32 is going for 69 degrees Celsius, something like this. And this is design of the steam velocity, and the same for pumps, operating conditions, cost analysis. You can add some aspects like interest rate, productivity, and so on. For MSF, that's for example here, productivity as, let's go for 3,000 meter cube per day. And here for MED, top steam temperature, top brine temperature, you can 70 degrees Celsius, as I think. MED is for 5,000, and MSF for 3,000. You can assign it. Okay, let's hit run, and we can see. Okay, let's discover a unit by unit. This is waste gas chimney. Therefore, we have to. This is waste gases mass flow rate. Okay, in order to desalinate, but first we have to check our. This is flash unit. We have to check dryness fraction. It should be not more than 1. Therefore, we have to return back again and reduce. We can reduce the steam temperature, or increasing the blow down temperature. Let's see, of MED, and watch. I'm sure we can go for dynamic system and watch this. Okay, we have to decrease more or increase top brine temperature a little bit. Let's go for 0.2. Okay, and flash. Okay, we have to check it again. Let's increase productivity for MED, or think for example 6,000. Oh no, we have to decrease the MED productivity. For example, 2,000, maybe less than a multi-stage flash, and watch the effect. Yes, 0.4. Yes, dryness fractions dropped by nearly 60%. Okay, for example, let's see, this is the flow rate of waste gases. This is mass flow rate of the waste gases. In order to desalinate totally about 5,000 meter cube per day, so we have to consume such amount of waste gases, and so on we can discover the pressure, waste gases, velocity, total losses, chimney, cross-section area, and so on. This steam generator load, let's see. This is waste gases mass flow rate. This is air mass flow rate. This is thermal power, and this is the exhaust temperature from the steam generator to be drained into the air, and this is the enthalpy, and this is enthalpy of the steam going to the brine heater. Specific fuel consumption, specific steam consumption, total exergetic efficiency, furnace height, and unit hourly cost. It's for the steam generator, we're going to consume about 63 US dollar per hour. Let's go for the brine heater unit. The brine heater we can draw out entropy, enthalpies, and so on. Therefore, we have to the pressure in the brine heater, top steam. This is top steam temperature going for the brine heater, and this is pressure, and this is mass flow rate, total mass flow rate through the cycle. Total mass flow rate of the steam through the cycle, it's about 7.4 kilogram per second. This is brine heater reversibility, number of tubes, area, and so on. And this is a top steam, outlet steam, condensate steam temperature, inlet steam temperature, mass flow rate, thermal energy, and so on. And this is recycled stream from the MSF, and this is the cycle temperature. This is the cycle temperature. This temperature is this one. Is the temperature is this is the cycle temperature, which is going on to the brine heater to be preheated. It's around 1.108. Top brine temperature 120. We assign this, and this is multi-stage flash. This is gain ratio, some total inlet feed water to the mixer, feed loss, because this is brine cycle. Brine blew down from the second splitter, recycled feed water mass flow rate, salinity, and this is profile. This is profile of brine profile, distillate profile, salinity profile, and sure, you can go here and this is brine profile, and you can draw some figures. This is per effect for MED, and this one, I think this one, just the profile, and this is for MED. Let's go for MSF. I think this is and this is for MSF. Yes, 20 stages. Distillate, accurate distillate, and this is brine profile per stage, and so on. So you have many parameters to address, and design parameters, areas, tube lengths, and so on. For this is flash cyclone, you can discover some pressure, entropies, condenser temperature, air condenser temperature, enthalpy, and so on. And this is the area, cross-section area of tube inlet steam of the flash cycle unit, and so on. And this is flash tank width parameter, total volume, enthalpy of the flashing. This is the liquid part at the bottom of the tank to be accumulated. Mass flow rate is 4.39, okay, and so on. This is MED, profile of temperature, brine, vapor temperature, and this is gear ratio for 8 effect. It's normal. This is pumping power. Sure, in MED you can discover the pumping system. This is brine pump. The brine pump is going to consume about 38 kilowatts. This pump unit. This is exergetic analysis. Total inlet exergy, total outlet exergy, and this is exergetic efficiency. And this is total exergy destruction rate, and this is pumping exergy. And this is some cost analysis, total water price, and so on. And we can go dynamically. I mean, we can set this out time to infinity. And let's see the effect of flashing pressure on the performance or the quality of the steam. Let's see here. Let's hit run and see. Okay. Okay, suppose we are going to decrease or increase the steam pressure. Increasing the steam pressure would increase the dryness fraction, sure, because we are going to increase the steam goes to the MED, as you can see here, and therefore we can surely we increase the volume of the tank and so on. This effect of on the gases mass flow rate. Let's see this parameter decreasing. Suppose we are going to decrease. Yes, decreasing. Yes, decreasing this will consume. It's the opposite effect. Consume more waste gases from the chimney. Okay, we can increase and control. I'm sure we can control many parameters. Let's go for turbine temperature and see this effect on the flash cycle. Let's see here. I'm going to decrease the turbine temperature. I am decreasing turbine temperature will increase the dryness fraction. Okay, as you can see here, and the same effect for dust stage brine temperature. I'm going to increase it up to 50, and you can see here. Okay, so we have here a dynamic model. It's up to you to assign your inputs based on which plant you are going to study, what is the performance, and you can enjoy many of physical properties and energetic data and design aspects, and so on. Okay, don't forget to download the azohost gases cycle for multi-surface or MED. But first, we have to discover some figures, the effect of on the dynamic fraction. As you can see here, this is our last run. This is total mass flow rate, top steam. Yes, there's an effect of, because we changed many times the pressure of the flash cycle. So this is decreasing or increasing the steam. This is top burn temperature effect, and so on. You can discover many parameters. This is mass flow rate of the gases, increasing and decreasing. Mass flow rate of the air, and so on. You can discover many parts. This is a volumetric. This is the volume of the tank of flash cyclone, because we increase the steam and decrease the steam pressure. And this is top burn temperature after decreasing and increasing, and so on. And finally, we can use waste gases. We are going to say, but simply, we can use waste gases instead of burning it through the air. So we can desalinate fresh water, seawater, and produce fresh water. And we can generate thermal power and electric power generation from such configurations. Thank you for watching. Don't forget to like, share, subscribe. You can download what you need on www.ritzlibrary.com. Thank you again.